Yeah, so welcome to the bootcamp on analog IC design under IEEE Open Silicon Initiative along with FOSSEE. And yeah, so this is the second day, and we will be talking about the physical layout and the DRC checks. So yesterday we saw about the schematic design using different open source tools, and Vipul explained about a brief about the semiconductor industry and so on. So over to you, Vipul.
Yeah, thank you, Sumanto. And good morning, everyone, and welcome to today's session. So, just to recap what we did yesterday. Yesterday we saw like how we start building our like IC integrated circuit from concept. We start with some architecture. In our cases, we are focusing on analog design. Our circuit has to be basically analog in nature. I think mostly you are from electronics background, so you understand basically what is the difference between digital and analog. So it all depends on how the signals are processed. If signals are processed in digital domain, we call them as digital ICs, and basically the process of them designing them is not little but quite different. As far as front end design is concerned, you start with Verilog, and then RTL and synthesis and timing. All those aspects are taken care in digital. But in analog, we our focus is mainly on preserving the integrity of the signal. So because signals are analog in nature, so their amplitude, frequency, all those parameters are well defined. And when those signals are to be processed, because they have been basically captured from nature, like is it a voice or like a image or something. So whatever information is captured from physical world, it has to be maintained. The integrity of that signal has to be maintained. So in that way, basically the criteria for analog designer is a bit different. He has to take care of a lot of specifications, like how well the signals are processed to analog circuitry. And that's where the process of designing those analog ICs become a little bit tedious. So first we start with concept, what kind of a circuit we need to design, whether it is an amplifier, filter, or some kind of a voltage source, current source. So there are different varieties of signal processing circuits required in analog design. So let it, because we are right now starting to build our, maybe most of you must be building your first analog circuit. Let us start with a very simple analog circuit, that is an op-amp. Op-amp is an operational amplifier, and it has some parameters. You start with some specification like gain, bandwidth, slew rate, noise, PSRR, CMRR. All those are the characterization. So you have to characterize your circuit. First, decide the architecture, characterize your circuit. In order to do that, you have to build, basically input it into some kind of a tool or software which will help you to analyze your circuit. So in our case, since we are using an open source process, so we started with Xscheme. Xscheme is a schematic editor. We entered our schematic. Yesterday I showed you like how we can build a schematic of a simple common source amplifier, use the components. Then once the circuit schematic is done, we build test benches around them. Test benches is like, since I mentioned number of specifications, so not all of them can be measured in single analysis domain. Like there are different kind of analysis need to be done, whether it is a DC analysis or AC analysis, frequency domain. If it is a time domain, you need to do transient analysis. And then there are advanced analysis. Like if you want to do noise analysis, then there are capabilities available in ngSpice, the simulator which we used yesterday. Or if you want to do RF analysis or some kind of a non-linearity analysis, harmonic distortion. So all those are come under the advanced category configuration. So all those analyses are basically performed inside ngSpice. In our tool flow, ngSpice works behind the scenes. You do not directly interact with ngSpice, but you, from your schematic, you generate a netlist. That netlist is then passed on to a simulator called ngSpice, and there is the analysis done. And whatever output is generated, we were able to see yesterday in the waveform viewer. Okay, so let me just before I start, I think I need also to share one thing with you. So yesterday I told you like whatever designs we are doing or you will be doing, that must be done inside this design underscore data folder. Okay. So let me show you what all files we built yesterday, and then I will show you where all that lies inside your Windows configuration. So this is the directory. We built these directories for schematic, magic, netgen, and yesterday whatever work we did was saved inside this directory xscheme. Okay, so all these files you are seeing in your Linux environment inside this. But as I told you, this is a basically a Docker container. So because this Docker container, let us say if you want to update it later on, or something, some corruption happens in it. So if this data lies inside this Docker container, everything will get lost. But we have made this Docker container like this, like all these files are basically saved inside your Windows disk, and you can basically see them inside your Windows directory. So let me show you where all those exist. So in my case, I have saved this Docker container inside directory, and I'm invoking it from this location as per the instructions given in the PDF document shared on Slack. And this is the directory where I can access all my design files, whatever things I was doing yesterday and will be doing next for Magic Xscheme. So these are physically available here. Okay, so I suggest, like, in case if you are like, this is a kind of a backup for you, just be cognizant of this. Like, if you want to copy it somewhere to access these files in future, or if you are updating your Docker or some changing your machine, so this data is always available here. It's not like if Docker is gone, your that file will be lost. Everything gets saved here, and you will see whatever work we will do today in Magic, we will get also saved here. Okay. Okay. With this, I will now move to my slide and give you just a brief background of what Magic is. Okay. So yesterday we saw these two steps, schematic and design and netlist. We also saw how netlist looks like generated from Xscheme. And then we built few test benches, AC, transient, and also DC analysis, and then did simulation with ngSpice. Okay, so once this step is done, it means, let us say, whatever specification you got from your test bench simulation, you are okay with that. Like, these are acceptable as per your requirement, whatever gain, bandwidth values you get, and your front end design is done, like you are okay with your electrical performance of circuit, then we okay. So thing is, like, that design is currently in the realm of basically simulation world. It's not ready to be fabricated. Like, as you must be knowing, basically building an IC means you have to implement your design on a silicon wafer. It's not good if you just do the basic simulation or try to build a very good circuit in front end, achieve very great spec. It means nothing, at least as long as it is not realized on a physical silicon, because that is the real world where your circuit gets realized and where you will be able to basically test it in the physical world. So in order to do that, we have to convert all those electrical devices and the way they are connected into layout. Layout is like, we are basically using their physical layers, how they will be realized on a silicon wafer, using all the complicated processes involved inside a fab. So there is a step, is a process on how to build a NMOS, PMOS, different kind of resistors, capacitors. All that information is captured inside a PDK. I think we also saw yesterday what PDK is. So PDK contains all that information, like how will those devices look like and how you can connect them. Like, there are different options, there are different metal layers based on the technology or a fab, whichever you are targeting. Like, in our case, we are targeting Skywater 130 nanometer. So this particular technology has, I think, there's a one local interconnect and there are five metal layers. So in total, there are six metallization layers which are available for you to make the connections. Okay, the lowest one is called local interconnect, and another layers are called metal 1, metal 2, metal 3, metal 4, metal 5. And so these are the layers. And then in order to make the connection between them, there are vias available, wires. So in order to, if you want to take your electrical connection from metal 1 to metal 2, it's not, because in physically when they are being fabricated on a wafer, they are not connected. So in order to make an electrical connection, we have to basically drill kind a hole between them, and that is in uh, basically semiconductor terminology, it is called a via. So wire has to be made between two metals in order to make an electrical connection. So all that information is part of our PDK. And in our case, the tool which we'll be using is Magic, and everything is pre-integrated, so you need not worry about it. Like, it is ready to use inside this Docker. Just invoke the Magic, and everything gets readily accessible, as we will be seeing in coming steps. And then with Magic, while doing layout, we will also look into DRC. I will talk more about it when we go into those steps. Okay, little bit history about Magic. It's not like Magic is a very new. In fact, it is, I think, the oldest layout tool which is available right now. It was developed in early 80s, and the idea about it started, I think, in 1970s. That was the era when, like, because as I told, the Moore's law was progressing very rapidly, and the number of devices or transistors which were getting integrated into a unit area was exploding. So people, they definitely thought like it would not be possible to do all this layout manually. So they wanted like software or some kind of automation to be done, and that's when this tool came up. And at that time, it was a very big kind of addition, especially to academia and researchers, because there was no concept of, I think in the 70s and maybe in 80s it started, but there was no concept of commercial tools at that time. Most of these things were freely available, so people you did use these tools to do their IC layouts and designs. It's only later like big commercial EDA companies came up, and they started charging a lot of money for their licenses. Okay, but then in last 5 6 years, since the open source IC design has made a comeback, so now the community has taken up these tools very much. Like the now Magic is like a very integrated part of layout steps, especially for OpenLane that is used for digital flow, and for Skywater 130 PDK. This is the recommended tool. So there is K layout also, but it is not very well integrated with Sky 130 PDK. It can be used with other open source PDK, but for Sky 130 PDK, Magic is the tool of preference for layout. And good part about it is like it is very lightweight, and it can be used on normal laptops. Otherwise, you cannot use Cadence or Synopsys tools on your normal laptops. You need very high resource intensive servers or workstation to use those tools, but with this you can do layout pretty much on your laptops, and it is open source, and it is very much suitable for at least for education and research. If those people who cannot afford like uh, paying big money to or resources or signing NDAs to commercial EDA tools, it is a very good alternate for them. So this is just a brief comparison how Magic differs from other commercial modern layout tools. So it is mostly command line. I think if some of you had worked with Virtuoso or K-Layout, you might find it little bit difficult or tricky to work on, but I can vouch, like if you do practice on it, it is very convenient tool to use. It does do get some taking up to work with it. It's not because you, if you have already used tools, you will be comparing it with commercial tools, Virtuoso or other tools. But otherwise, it is a very convenient tool, and it has a different way to interpret layout data, because the other tools, modern layout tools, they basically work. They define everything inside them as objects. Like a MOSFET is an object, or different devices are an object. Even the metal layers or the wires or vias which are used, they are objects. But inside Magic, the most of the things are basically interpreted as like they are, you are doing a painting, there are cells and you are painting the cells. So it is a little bit different approach to do, but we will see. I will give you some guidance and how to work with this. One very good feature with Magic is DRC. Okay, it has an inbuilt DRC, and it is very convenient. I think this feature even the commercial tools cannot compare Magic to, because with commercial tools you have to integrate an external DRC tools like a Caliber or a PVS from Cadence, and then you have to pass on your GDS to those tools, and then DRC is run. But it is in Magic, it is a real time DRC. As you are doing your layout on the go, you are seeing like how many is whatever command I have executed last, whether it has caused me a DRC error or not. You can see it live, and there itself you can make a rectification of your error or whatever mistake you have done while moving the layers. So Magic is very good for small to medium layouts. Okay, and if you are talking about commercial scale ICs where you are talking millions and billions of transistors or devices, obviously you have to move to commercial layouts. But for small analog, at least for analog layouts, it's sufficient, because analog layout designs do not contain too many devices like in the quantities which I mentioned. So they have pretty much small numbers, and it can easily handle them. Yeah, I think rest of these things are standard. So these are some of the commands which we will see how to execute. Not all I will be covering, but I think most of the work can be done with these commands. So these I will be putting it on Slack for your reference, so don't worry. And I will be executing few of those commands today to tell you like how we can put the devices, move them, and make the connection, all those steps. And so this will be kind of your go-to reference, apart from the other resources which are available. So this will be useful for you. So these two slides you can refer to whenever you are trying to work with Magic and are stuck with somewhere. Okay, so these are the steps which we'll see today. So yesterday we built a schematic, And in order to do a layout, we will generate a netlist from this schematic. This is a step I will show you while executing this. So this step will generate a netlist which is compatible or which can be imported inside a Magic to start building our layout. Okay. So this is the first step. So once this is run, this netlist will be generated. A unique point to look into this netlist is like it will be the connections or the devices for this circuit will be captured inside this sub-circuit statement. Okay, and this happens because we have enabled this menu option here, LVS netlist top level as a sub-circuit. So only this netlist can be imported inside Magic to start building layout. So once that is done, we will invoke Magic. So this kind of window will open. So this is your main sheet where all the execution of your instances and their like connection between metals layers to different devices will be done. And then there is a very small window which opens at the bottom. It is called console. So all your commands which are to be executed through command line will be run through this console window, and they will get implemented inside your this Magic sheet. So yeah, this is the how the window will look. This is your main layout area. This is the palette. All the layers which are used for layout as part of PDK are seen. So this is like image from my one of my old like versions of Magic. So but now you see it a little bit different way. And this is the console where the command will be executed. And the first thing which we do when we open Magic is import Spice netlist, the one which was generated from Xscheme. And when it is done, all the devices which are available in that netlist get instantiated inside this blank sheet. So whatever devices, MOSFET, resistor, capacitor, everything comes on this blank sheet. And now the actual task of a designer starts. Like he basically first places all these devices, segregates them as per the area where he want to place them. And then if you want to change the properties of these devices, like if you want to convert them into fingers, like these are very big transistors, which are very long, but you want them in smaller sizes. So you can change those properties here. This we will see, and then place them as per your wish, like the way you want to place, whether the way these devices are arranged in your schematic, or is there is some other consideration. So you move those devices and place them, and then start connecting them using metallization layers, metal layers which are available in this PDK. And then this is how your final layout will look like. Okay, so now let us go to the actual implementation. Any question till now?
This Shubhikesh is asking like I'm using local host as remote desktop rather than in Windows. Is that fine? I guess that is fine.
Yeah, I think that's okay. As long as you are able to open this Docker and execute your tools, I think that's fine.
Yeah.
Okay.
Cool.
So yes, yesterday we were working in this directory because we were working on Xscheme and simulation. So as I told you, it's a good habit to maintain your databases separately. Don't try to put everything inside a single directory, because as time goes by, as you start building more and more steps and building more views, this become a bit cluttered, and it gets difficult to handle. So it's a good habit to make different directories and put your different design files as per the step you are executing in them. So we were doing schematic simulation, so we were doing in Xscheme. Now we will move to Magic. Okay. So yeah, so there are some files lying here because I was working there. But today we will start from blank here. I will invoke Magic here, and this kind of window will open. So there you can see there are two windows which have opened. So this is your main window where all our execution of layout will be done. We will actually build our layout here. And then there's this console window. This is a command line interface to Magic. If you want to execute some commands, and there will be a requirement for that, because not everything is convenient to do through like a mouse or through cursor here on the Magic sheet. So there are some commands which are very well executed through console window. I will show you how to do that also. So it's better to open this configuration of Magic in this way. Your main sheet lies on the top, and console lies on the bottom with the small view so that you can easily execute your commands here. Okay. So the first step is we want to import our netlist, which was generated yesterday. So, okay, so that netlist lied inside Xscheme folder simulation, and inside it there was a simulation folder. So we will go there, Xscheme. Okay, so I think I need to tell you how to generate this Xscheme schematic file also. So let me start with that. This is our schematic, and the other schematic which we use were the test bench schematic, which included the symbol of this, and they were used for simulation. But they were not our actual circuit, which we will be comparing to layout, because it included several other things: input sources, output load, etc. So those are not part of our actual circuit. Those are just part of our test bench. Our actual circuit lies this much only. Okay, so this is what we want to lay out on a silicon wafer for fabrication. So to start generating a netlist, go to this option and just enable this option, LVS netlist, and then press netlist. And then this netlist would have got generated. In order to see that netlist, go to simulation and edit netlist. Okay. So this netlist got generated here. But first, also do remember to change your path of this netlist directory also, because this is getting generated inside .xscheme folder. But I wanted it to generate inside the local simulation folder inside my xscheme directory. So let me set this path first. So this is the directory where I want all my netlist file to be saved. So I will select this. Now I will again do netlist and then simulation and edit netlist. So now you see this file. This is the netlist file from my schematic, and it got saved inside this path which I had just selected. So this is the netlist which I will import, and it can be used for building layout. Now let me go back to my magic setup. Go to file, import spice, and this path where this the last netlist was generated, and this was that netlist, CSM, and open. Okay, so as soon as you import this, these components got generated automatically here. Okay, so this is a good part, because it's also possible, if you want to do it manually, you can go into these options and start instantiating your devices separately. So the good part of Sky 130 PDK with Magic is like everything, all the pieces are available here. Whatever, if you are doing some other kind of a design, you are using diodes or LDMOS or some other kind of all those available here. And this is a way, if you want to instantiate them manually, you can select the device, change their properties, and that device will get appear here. But if you are doing a complex circuit, like the circuit which has many components, you would avoid putting them each manually here, because there is a chance you might miss something. It's a good habit, a good practice to import that netlist which actually you use for validating your front end design, and import everything here. So this way everything got instantiated here. So what is here, so okay, so now just focus on the command. If I want to zoom in, I will use Z on my keyboard, and I can use mouse to scroll. If I want to zoom out, I can use Shift Z. And if I want to use a full view, like I want to see everything in a full view on my magic sheet, I will press V key on my keyboard, so everything is appears in a full view. And one important thing about magic is there's a concept of building a box. Okay, so this box, wherever you will come across this box command, like if you have to draw some layer, or if you have to select something, a box has to be built. I will show you later when I follow steps, but how to build that box. In order to build that box, press the left mouse button, and the box will start. Like this box appeared here. And if I want to change the size of this box, I will take it to that location, the cursor of my mouse on in that part of a sheet, and press the right mouse button. So this box will get shaped accordingly. Okay, if I now want to build a box in this location, I will press a left mouse button and then right mouse button. So this box start appearing like this. So we will see how this box will be used later on. But this is how a box is, and these commands are being mentioned in those readme or a PDF steps which I have given in the slide. I think that will be shared with you, so you can see how that is to be executed. So the first part is we can see all these components are kind of overlapped each other. So first I want like to separate them. So in order to do that, I will focus on this A part. So I will build a box. And if I want to zoom into this specific part of my layout, I will press Control Z on my keyboard. Okay. So only that portion will get zoomed. If I further want to zoom, I will press Z. So I see this is my poly register, and I want to kind of separate it from this portion for now. So what I will do, I will select it. How to select it? Bring your mouse here and press I key on your keyboard. So whatever instance is under the area where I key was pressed with cursor there, that will get selected. If I want to move it, so I will take my mouse to a location where this device has to be moved and press M key on the keyboard. So this device will move to that part. Let us say I want to move it on the top. I will again select it and press M key on the keyboard. So this poly register will move to this path. Now I want to move this NMOS. I will select it using I key and I want to bring it to the lower bottom side. So I will press M here. So it will move here. So I still want to move it to the bottom. So I will zoom out and press M key. Okay. So this is how I have put them. So this is how you move the instances on Magic. And these are the pins. These pins again come from the schematic in the netlist because we have defined these pins. So right now we only have these two components. But I can see this NMOS is not looking proper. Like it has a very high width, big width. I would like to divide it into separate fingers. So how to do that? I will select this NMOS using I key on the keyboard and then press Control P on the keyboard. So it will open the properties of this NMOS. And I can see there's a width of 30 and length of 5, but maybe I would like to divide it into 6 fingers. So I will do 5 here and fingers as 6. Okay, and apply. So you can see this MOS, which was 30 by 0.25, got converted into 5 by 0.25 and with 6 fingers. So again, I think this I would like to move on the top. So select this instance and then use M key on the keyboard. And if I want to focus on this particular area, I will build a box around this area and press Ctrl Z. And again, if I want to do a fine moving of this device, I can use M key. Or there is another option also if you want to move this instance which has been by small steps. So you can use the key numbers on your numpad of your laptop or your PC. There are key number 4862. If you want it to move to the north direction on the top, so press key number 8 on your keyboard. This is for fine moving. If you want to move this device by small steps, so pressing 8 will move towards the north direction. Pressing 4 on the numpad with key number 4 will move it to the west direction or the left hand side of your. If you want to move it to the right hand side or the east direction, use key number 6. And this all while this instance is selected. And if you want it to move to the bottom direction or the south direction, you press 2, key number 2 on your keyboard. So you can see it moves by very small steps. So right now I want to move it further to the north. So I am pressing key number 8. Okay, so let us say this is okay and I'm happy with it here. And to see the full screen, I will press V. Now to move these keys, I will again build a box around these pins and press key A key on the keyboard. So it will select everything, all the shapes which are selected inside the box. They are selected. And to move them, I will again press M key on the keyboard to with the cursor at the location where these selected shapes has to be moved. So it will move here. Okay. So now this is what is called placement step, where you are trying to place your components appropriately as per the requirement of the way you want to place these component. And I think most of these things are done. So to just see the full view, I will press FV key on the keyboard. Okay. So now let us focus because the next step is the placement is done. We would like to make the connections, the electrical connection between different terminals as per the schematic. So let me open schematic also so that I can show you. So this is my schematic, and these are the two components which I have placed in my layout. The poly resistors on the top and the NMOS on the bottom. So this NMOS was not looking appropriately during layout because it has a very huge width. So I divided it to 6 fingers so that it is dimensions becomes optimized to be placed. And also my area is saved because these things are to be taken care by the layout engineer. It is a task of a layout engineer to take care like how well he can make an optimized layout so that it is also it works efficiently also, and it does not waste too much area also, because on silicon everything is you have to pay cost for that. If you are building same area in larger same layout in a larger area, so obviously the cost of a chip will be more, and it's a very costly affair, so you want to optimize the layout also. So that's why we try to do this step by dividing our big and MOS with 30 by 0.25 dimensions into a smaller width so that the area of that NMOS becomes optimized. Okay, so these devices were placed. The next step is to make these connections, the wires. So let us see how to do that. So before that, I have to identify which are the what are the which terminals of my NMOS. So these pink color of layers which are shown are the gate terminals, and the other terminals I can start taking this on the leftmost terminal as a drain. So this become one becomes source, then drain source, drain source, drain source, because they have been basically attached. That the two terminals, like the source terminals of two fingers, have been overlapped, so they becomes one. Okay, so electrically this does not make any difference, but from area wise point of view, this makes your layout more optimized. So this has been done. So let me assume this is my drain terminal, this is my gate terminals, and this is my source terminal. But another issue which I see here is like the drain, the electrical connection to the local interconnect and metal one layer from the gate have been put on either side, on the top also and the bottom, but I want all of them to be on one side, either on the top side or on the bottom side. So the good thing about Sky 130 PDK is like these all features have been implemented inside the P cells. So I will again select this instance and use the properties control P, and there is an option you can see connect gate together. So what it will do, it will connect all the gates together. Let me show you. Apply. So it connected both on the top and the bottom. All the gates have been connected. And but I do not want these gates to be on the bottom side. I want like it's okay if I have them on the top side only. So I can disable this option, add bottom gate contact. Okay, so I now have gate connection only on the top side. Okay, so all these are the features which are available inside the properties. So based on your requirement, maybe you have some other unique requirement for your layout. If you want a gardening or not, if you want the gardening only on the left side or maybe in the on the three sides but not on the fourth side, you can enable all those features also, the VRs and all those features. So these properties are very well implemented inside this PDK, and as per your unique requirement, as per your layout requirement, these can be played with. Just try once you are trying to build your layout, and if you get stuck somewhere, like let us say if you want to bring a metal one out from this NMOS, but it's not possible because there is already a metal one going from somewhere. So you can change the properties of this NMOS P cell, and you can remove some of the layers which are coded inside P cell so that you can make that connection accordingly. So these things are to be used for a kind of advanced requirements. Okay. So once this is done, let me again see a full view. And now let us start building our connections. So the first connection which I would like to make is between uh, the lower terminal of this resistor and the drain terminal of my NMOS. This one, this is connected to the out terminal node. So this is my terminal of resistors, and I have selected this as the drain terminal of my NMOS. So I will try to make a connection between them. Now, first, for making a connection, I have to see what layers are available and whether I can use those layers to make connections or not. So let us see how we can see the layers. And here this console window comes into picture. So in Sky 130, the lowermost metal layer or the conductor layer which can be used is called local interconnect, and it is used by a name called Li. After that starts the second layer, which is called metal 1, metal 2, metal 3, metal 4, metal 5. So there are total 6 layers. The bottom one starts with local interconnect, and then the above that lies metal 1. So I have to see where the local interconnect layer is. So for that, first I will what I will do, I will basically make all the layers disappear from my layout. For that, the command has to be typed in the console window. It is called C no star, and everything becomes invisible in my layout. Okay, so now I want to see one by one which layers are available where. So let me first start with poly. So this is my gate connection, and now I will see local interconnect Li. So this is my local interconnection layer. So local interconnect lies here also, here also. But problem is between them, there are guard rings, and on guard ring also there is a local interconnect layer. So I cannot, and there is local interconnect layer on this gate connection also of the NMOS. So I cannot use local interconnect to connect these. So okay, so I will have to move one layer top in that hierarchy. So let me see whether there is a metal one. Yeah, so there is a metal one here. Okay. So I can use metal one, and there is metal one here also. I can use metal one to make the connection between drain of this NMOS and the lower terminal of this resistor. But the issue is there is metal one over this gate connection also. You can see. Let me again show you, by making other layers invisible. See no star and see metal one. So now you can see what is the purpose of using this console. Okay, so this is that. So there is metal one on these terminal drain source both, and this is metal one here, and but there is a metal one here also. So I cannot use metal one because I have to take connection from here to here. So next option for me is to see whether there is metal 2 available here. Okay, so metal 2 is available, but it's not used in these layouts till now. So I can use metal 2 from here drain terminal to the lower terminal of poly resistor to make this connection. Okay, so that's what I will use. Now let us start how to build that connection. So in order to see all my layers back, I will do C star, and everything starts appearing again here. Okay, so in order to make a connection with metal 2, first there are only layers up to metal 1 here. So to make a connection between metal 1 to metal 2, I have to add a via. As I told you, to make electrical connection between two adjacent layers in a stack of a semiconductor process of this CMOS technology, we have to use vias. So there is a metal one here. I have to add a metal two, but before that, I have to add a via. So how to add a via? I will build a box over this region where I have to add a via, and then I will go to this menu and I will add a via one. So via one is basically P cell which has been created in this PDK for connection between metal 1 and metal 2. So as soon as I select via 1, so you see this via has been added on this region, the box where I have built a box. So just to see what has been done, see no star, I will make everything invisible, and then I will see via 1. You can see VIA1 has been added, and then see metal 2. Metal 2 has also been added. So let me show you by doing C no star and C metal 2. Yeah, so this is metal 2 and this is VIA1. So they both look pink, but these layers are available here. So now this is an additional layer which I have added. And similarly, I have to add these layers here also, or between these terminals. These are the drain terminal, alternate terminals of NMOS. These are the drain terminals. So I will have to add via here, here also, because this connection has to be made using metal 2. So let me zoom in to this region. I will build a box and then using via 1. Similarly here, via 1, via 1, via 1. Okay. So now all these terminals of NMOS has been electrically connected to metal 2 through local interconnect metal 1 and via with the via in between and metal 2. So now there is metal 2 layer over these both terminals. Let me zoom in just to verify. I will again do and see if metal 2 via1 has been added. Yes, via1 has been added to both the connections and also metal 2. Yeah, metal 2 has also been added. I think it's not properly visible, but it is added. Let me show you again. Yeah, these are the metal two. So now we can make an electrical connection between these two regions. Before that, we have to connect these four because these are although metal 2 is there, but they are not electrically connected together. So first we have to connect them together. And how to do that? First, so for that we have to build up a box between this region where we have to make a connection using metal 2. So this is how a box has been built, and I have to make a basically paint this region using metal 2. So how to do that? Go to the left or to the right hand side of your window and look for metal 2. So this is metal 2, and I want to basically paint this region using metal 2 because I have to make connection between these four terminals. So take your mouse over metal 2 and press the mouse wheel or the center button if you that is available in your mouse. So this region gets painted using metal 2. So this is how you basically paint the box, or you make a metal connection. This in this case, this is a metal connection using metal 2. Just to say again, okay. Now see, this metal 2 connection has been made between two individual terminals, and now only step remaining is I have to make connection between. Yeah, it is there. And paint again, build a box between two regions where the connection has to be made, and paint it with metal 2 again to check it. Okay, now you can see this connection has been made metal 2. Okay, so this is one terminal connection we made. So now this is the out connection. Then the remaining is the input. Let us focus on that. So the input connection has to be made through the gate. So gate we saw this is on metal 1, Let me show you again. And there is no metal one on the guard ring around the NMOS. Okay, so you can see there is no metal one around the guarding, but there is only local interconnect layer here. So definitely we cannot use local interconnect to make this connection because then they will get shorted, but we can use a metal one. So what I will do within this view itself, I will make a box from here to, let us say, this part, and I will paint it with metal one. So this connection has been made, metal one to the gate. To see again the full view, V. Okay, so this is input and this was out connection. Then the VSS and VDD connections are to be made. So for VSS connection, zoom in. Again, the same issue comes here also. But here we need not use metal 2 because this is a local interconnect and we know there's already metal 1 over this part. So we can directly use metal 1 to bring this terminal outside and make a connections. So I will, let me, yeah, so there is metal one on this source part of these NMOS fingers. So just make a box and paint it with metal one. Similarly, if you want to copy it, let us say I do not want to paint it again and again, but I want to copy this, whatever layer I have added, I want to copy, just select it using, bring the cursor over this layer and press S. And if you want to copy it, make it to the location, bring the cursor where you want to copy this and press C key on the keyboard. So it will get copied. Similarly here, okay, maybe later we can see, but this is how a DRC error comes up. As I mentioned earlier, Magic has a very good feature, like it can detect a DRC error on the go. So as soon as I put this layer here, so it is showing me there is some DRC error. It will highlight you there is an DRC error due to this metal one layer being misaligned with the this finger source terminal. So that's why this error is coming. So in order to rectify this error, what I can do, I have to align this layer with this the finger uh, source terminal. So what I will do, I will select this, bring the cursor S key, and I have to move it with small steps. So rather than doing M command, I will use key number 4 on my numpad. So as you see, this layer moves to the right. This error is getting disappeared, but there is an extra layer here. That's why this error is still there. So what I will do, I will select this layer using A key on the building a box, select the region inside this box using A key and then delete it. If I to in order to delete it, press D key on the keyboard. Okay, but
Uh,
there's,
Vipul, so is there a way to undo the your steps?
yeah, you can press the U key on the keyboard.
Okay.
Yeah. So let me show you that these were the steps I did. If I want to undo them, press U key on the keyboard. So those steps will get undone. Yeah. So this is how you can undo those steps, pressing U key on the keyboard. If you want to redo the steps, you can press Shift U on the keyboard.
I would request other people to type their doubts, as these are very important steps in Magic.
Yeah. No issue. Maybe if I think if anybody has step, you please contact me on Slack. Maybe I can guide you there also, and I will if these are some specific query, maybe I will make a short video of the steps and share on Magic on Slack.
And that will be great.
Yeah, yeah. Okay. So as you can see, it is still showing me some error. This DRC. This is the menu option where DRC errors are seen, because there's a small part of this layer which is still existing. So that's why this error was coming. So let me remove it. I will bring my cursor over this layer, press S or press A and delete it. Okay, but I think it is doing something else. So let me undo all those steps.
Another thing I would ask Vipul, can you point out like how will the new people understand the meaning of this DRC errors?
Yeah, so
There are
if you want, yeah, that's what I'm telling you. Just build a box over the region where you are getting a DRC error, and press DRC on in the console DRC You see, so it is telling me what how these errors, whatever errors are coming here, how they are coded inside your PDK. But it will just give you a brief line about that error. If you want to understand more about that error, then you have to go to the documentation of Skywater. Let me also take this opportunity to maybe show you how the documentation looks like. Yeah. So in order to understand what is the meaning of those DRC errors, so there's a design rule section here, and error messages. Okay, so this basically you have to go through search whatever error you are getting if you want to understand more about the meaning of that error. So this is the uh, area, or this is the menu option where you have to go and search for that specific error. Maybe there are thousand kind of DRC errors coded inside this PDK. Okay, so maybe you will not be able to understand all of them, so it's better take a help of this documentation. And now I think with the help of AI, maybe it becomes even more easier. Like just try to find out if you can make sense by putting that error, whatever you are getting in DRC, into any AI tool of your choice, and try to understand what that error is, and then come back to Magic and try to rectify it. Okay, I think now this error, it will take me some time to rectify it, so maybe I will do it later to avoid taking too much time. So just what I will do. Yeah. So let me quickly try to make the connections. So this is the metal one connection which I brought to the bottom, and now I want to connect them together. So for that, again, I will make a box and then paint it with metal one. So now these source terminals of this NMOS are being connected together through this metal one connection. So, and okay, one more thing. For this NMOS, we can see even the bulk connection is being connected to your source VSS. So for NMOS, in this layout, the bulk is being represented through this guarding. So it means we have to make connection between this source and this guarding also. So in order to, but this guarding contains of local interconnect layer, LI layer. So, and this source connection is through metal one. So we have to put a via between local interconnect and metal one layer here. So how to put it? Again, make a box, go to devices, and the via called is mcon between local interconnect and metal one. Okay, so now after this via, this select connection has been shorted and this has been made. Okay, so now the only remaining connection is of this drain, the in terminal. So let us focus on that. So this drain connection has to be made from this upper terminal of a resistor. It already had a metal one, and this is a local interconnect, so we are not worried about overlapping it. So we can just make a box and paint it with metal 1. So this becomes a drain connection. And one connection which is remaining is, let me show you, the bulk connection to this poly resistor. So this poly resistor has a bulk connection. I think it must be made in a P well or some this kind of a structure. So to make it immune to noise. So this VSS connection has to be provided to this bulk connection, that which has again represented using a guard ring around this poly resistor. So this has to be electrically connected. If it is not done, it means there will be an issue in LVS, because this is a specific node or terminal which is provided as part of PDK for this device. So for doing that, what we can do, we know this is VSS connection, and this VSS and this, even this guard ring around this NMOS is all connected to VSS. So rather than maybe we can make connection through this region, local interconnect layer, because they both are to be on VSS, and paint it with local interconnect. Okay, so this makes connection between these two guard rings for NMOS and for also this poly resistor. So now electrically all the connections have been made. Now in order to make connection for LVS, because we have to identify by which connection is represented by what name, similar to the pins which were used in schematic. So similarly, these pins have to be added to this connection. So this was my input. So I will select this input pin and move it here. Okay, let me just relaunch it. I think some issue is there. Commands are not so okay. Once layout is done, just remember to save it like this. Save and auto write. It will automatically take the name from the netlist, so you need not rename it. Just auto write, and it will, this layout will get saved. So let me reopen it. When you open it first time, it will open like this. Like you will not be seeing in inner layers of this layout. So press X key on your keyboard. Everything gets again becomes visible. Okay, so this command was not running. I will select my pin and move it here. Yeah, so this is how it moved. So now again this DRC, it is showing DRC error, maybe because these two layers are very near and they are violating DRC error. So in order to remove it, I will select this pin and move it to the top direction using the key number 8 on my keypad. And as I move it, that DRC error disappears. So this is something which I also find very intuitive about Magic. I think this kind of ability is also lacking in some of the advanced layout tools, but it's very good here. Similarly, I want to take out connection pin here, select it and move it here. But now issue is like this out connection we had made on metal 2, but this pin is on metal 1. So I will make a metal 2 layer here, paint it with metal 2. And but this pin is on metal 1. So in order to have an electrical connection, I will put a via over this region. So this metal 2 gets connected to this metal 1 pin through via. Okay, so this is metal 2, pin was on metal 1, but I had put a via, so these are electrically connected. Similarly, VDD, I will select it and move it to this part. So this VDD connection, and similarly VSS, I will take it and move it to this part. If I want to overlap it, just I will extend my metal one box over here. Okay, so this is a very basic layout of common source amplifier. So I think we have seen how to place these components and how to change their properties, put VRs and make the connection. Okay, this is a kind of a very crude layout, but I think this gives you a good idea of like how to start with. And I must tell you, like some of you, if you have experience of commercial tools, you might initially find it very like kind of a different difficult or might not find it very easy to work on. But again, layout is all about practice because it is very focus intensive work. So as I mentioned yesterday, they are specialized people in industry. They are working as layout engineers, and they are very well, basically they only do layouts. So, but for small kind of circuits like this, and for this program, for this tape out program, I think for small circuits, okay, you can start building your own layout. It does not have to be a perfect layout, but start building. I think more and more you work with layout, I think the better you become at it. Yeah. So I think that is all for today from my side. Now we can have any if queries we can discuss.
So first of all, I would be having some queries like
Yeah.
so from the PDK perspective, so for example, we are currently using the automated thing of importing the layout and importing
Mhm.
the list. But if someone
Mhm.
wants to do it from scratch, for
Yeah.
example, if someone needs a resistance of so and so value,
Yeah.
so how will he or she proceed with the calculation and directly jump into the layout? Is there a way?
Yeah, so let us say if you want to build a resistor of let us say 5 kilo ohms, okay. So there are multiple. Let me again show you the PDK. So the starting point for you will be this PDK. You have to go inside this PDK documentation and then find the devices. What all devices are available here? Yeah. So Sumantro, can you see?
Yeah. Okay.
So inside the PDK documentation, you have to find like if you are talking about a resistance, so there are different type of resistance available here. Okay, so each resistance has their own properties. Like there are high density resistance, they are maybe there are low temperature coefficient resistance, low voltage coefficient resistance. So based on your requirement, like if you are building a very high sensitive design, you want your resistance to vary too much due to the effects of fabrication process effects. So based on that, first you have to identify which is the resistance which I want. Then you have these values available inside PDK. These are sheet resistance values of different resistance. Using these sheet resistance value and the desired value which you require, you have to calculate what are the width and lengths I have required for that device. And then once you have selected those values on your like by doing hand calculation on pen and paper, then go inside the schematic simulation, and while selecting the devices you can decide the length and width as per your manual calculations and arrive at a particular width length for that resistance. So that's how you do. Once that has been used in your schematic, that information will automatically get passed on during layout when you import the netlist.
I see. Okay. So these values are like ohm per micrometer, right?
Yeah, ohm per square.
Ohm per square. Okay.
Yeah, so these are sheet resistance values.
Yeah.
Yeah.
Anyone else has any other query?
Sir, I had one query.
Yes, please.
Sir, are there any other like open source tutorials available for analog layouts which explain layout of amplifier in more detail, like two-stage Miller op-amp?
Yeah, I think I have seen on YouTube there are like lot of resources available. In fact, for Magic also there are good videos available. Okay. So if you want, I can share. Please specify your query on Slack. Accordingly, maybe I will share you the resource what you want.
Yes, sir. If you find any such magic tutorials for layout specifically for Miller op-amp, please share it with us.
Okay, sure. I will. I will try to find and share on YouTube. And acha, okay, one more thing I want to share. Maybe I will do it quickly. So, so there are manuals available for everything. The tools which I have used till now. Like yesterday, we were using Xscheme. So there is a manual available, complete manual. So I can understand it's very difficult to understand this manual at first go if you are fresher. But again, I will suggest you, like, using the power of AI nowadays, you can pretty much easily interpret these manuals. Wherever you are stuck with Xscheme, try to feed this manual to AI and try to find the solution to your queries. This is for Xscheme. Uh, And this is the website from the developer of Xscheme, Stephen Shippers. I think he has provided a lot of information here how to use Xscheme. I think for you, yourself, you do not need everything here right now. But still, if you are get stuck somewhere or if you want to find some solutions, these are the resources where you can find for Xscheme. Similarly, for ngSpice, there is a big documentation for ngSpice also, where all the features and how to use which command or understand any specific command where you are stuck at. This is available for ngSpice also. And also Magic, which and this is the ngSpice website. So just like because these tools are open source, that's why everything is available online. But if you are talking about commercial tools, this kind of information manuals are not easily available. Uh, so just try to, because these are the basically the places where you have to go wherever you're stuck. Okay. Even I have some experience with open source tools, but still, if I am stuck somewhere, these are the resources which I take care of, help of. And similarly for Magic, this is the place where all the information about Magic or different command or etc. are available. So yeah, this is for your reference. If you want to go into more details or want to understand something specific which is being used, so these are the resources which you can take help of. Besides that, as discussed, I will share some online tutorials on Magic on Slack. So any other queries?
Any other queries, everyone?
Sir, I'm not able to move the pins. Whenever I press I to select that instance, it shows me the top cell window selected, and I cannot move any of the pins.
So if you are seeing a top cell window, press the semicolon key on your, because what happens sometimes while building a box, Magic takes selects everything and takes you to the top cell of the hierarchy in your layout. So if you want to break that hierarchy, press the semicolon key on the keyboard, and then you can choose the individual components in your layout. Just try this. If any face any issue, please tell me on Slack. I will try to share something on that.
Okay.
And also, please try thinking about the circuit which you are planning to do, like an op-amp, band gap reference, whatever you want. Maybe if you want to try, maybe you can just design a two-input NAND gate or something like that also. Even that is okay, because the idea is to give you an experience of this flow, build a confidence on using these tools, so that later on when you are confident, you can use them for making complex design. And a big part is like you have an opportunity to get your designs fabricated. I think it's not all every day like this kind of opportunity comes to your door. And if you have any ideas to share, you may please contact me on Slack. I maybe I can help you choose a circuit so that that can be done in this limited time period of around 16-17 days. Yeah. Okay, then thank you. I think Sumanta, we can conclude today.
Okay, thanks, people, for being our uh, guest speaker. Yeah.
Okay, thank you, Sumanta. Bye. Have a nice day, everyone.